In the last video, we talked about what happens to the length of some piece of biological tissue, like a tendon, if you pull on it. But there was this little problem, and the little problem is obviously something that's thicker is going to be stiffer than something that's thinner, even if they're made out of the same material. So there's a way to normalize for that, and that way is to not look at force and change in length. But what we're going to do is the exact same experiment, but instead I'm going to plot the force divided by the area, and that's the cross-sectional area of say this Achilles tendon that we're stretching out. And then down here I'm going to plot the change in length but I'm going to do it as a percentage of the original length, because this is one of the other technicalities. A really long tendon is going to stretch differently than a really short one. So what we want to do is we want to look at force over area as a function of change in length as opposed to as a percentage, relative change in length. And there's special names for each of these terms, which I have written right here. Stress is the technical term for this. And then this here, the percentage change in length, is called strain. You occasionally these are written using Greek letters, epsilon and sigma. I'm just going to write in this class stress and strain because it's quite easy to get these two mixed up. So we can do the same thing, and as a reminder, what we're visualizing here is, suppose you grab a tendon from a cadaver and then you just pull on it. So now all we need to know is, number one, what's the original length of the tendon? Maybe it's 4 inches long. And number two, what's the cross-sectional area? So if you took a little slice of it like this, what is that area in like square inches or square centimeters? And then we can do exactly the same thing. If we pull on the tendon, it gets longer, and it is going to do that as a function of how hard we pull on it. And just like last time, this slope, the units are different, but the interpretation is the same. This slope, how steep is this, tells us what the stiffness of that material is. So something that's made out of something that's intrinsically stronger is going to maybe have a slope like this, right? Bone maybe might look like this, whereas tendon might look like this, whereas, I don't know, skin, something really soft, might look like this. And really, this ought to be straight if I'm doing a good job illustrating here. So yeah, that looks good. There's a few interesting features in a graph like this when you're doing this. So let's imagine we start out with our tendon completely relaxed, and we start pulling on it. There's this little baby region over here called the toe region, because it kind of just looks like a little toe. So I'll write that out. Toe region is that part. And then there's a big long portion in here called the linear area, or linear region. Sometimes it's also called the elastic region. The reason being that if you got an idealized spring or a rubber band, it would look exactly like this. If you've taken physics and you know that the force of a spring is negative K delta X, that's this K, that constant, is the slope. This is a straight line, right? So like f as a function of delta x is going to be a linear function here. But if you haven't taken physics, don't worry about that. This is where our piece of tissue, our tendon or ligament or whatever, is behaving as this sort of like idealized spring. So you stretch it out, and then you get more force per unit cross-sectional area. Then if you keep yanking on it, though, something interesting starts happening, which is this. It will start going like that. So there's a few, and I should probably, let me correct that so my box labeling here is correct. You might go, you'll go off from linear, and then something strange happens. First off, you get to this point. This is an important point. It's called the ultimate strength or ultimate stress. Write that, ultimate stress. Because it's the greatest amount of stress in this physical sense that this material can maintain. But what's happening here, the reason why our length change is going off from this, linear extrapolation, is that the material is actually is becoming, it's called, the technical term is called plastic. This is why plastic, as you know it, is called plastic, is because it does this. It's like it's stretching out, and then down here it's actually really getting elongated, and it will not return to normal length, and eventually it breaks. Usually that's just labeled failure. So inside the body, if you are a healthy person, you're going to be operating in this region. And I suppose I should annote that plastic region that's like here. And this final region out to the right is called the yielding area. That's like, when you're driving, you yield to somebody. It's you're giving way. You're giving up, in a sense. So if you get up to here, this region in biological tissue, you are in bad shape, because what that means is there is physical damage happening inside the tissue. So this is a stress strain curve, and it's a really, really useful tool for learning how different biological tissues respond to physical stresses that we put them under. If you're wondering, say, about the term stress fracture, it literally comes from this physical interpretation of stress, meaning too much force over too small of an area. In the next video, I'm going to go over this again and talk about some of the more interesting features that we can learn from the stress strain curve of a particular material. So I'll see you in that video.